In this video, we're just going to do some practice for intermolecular forces. In the previous lecture, we just did the notes, but there weren't any examples for you guys to practice. So first one, let's say you were asked to determine all the intermolecular forces acting on. First one, let's say I had nitrogen trichloride. So the first thing that you want to do, how we want to approach this problem, first thing is to look at it and figure out if it is polar or nonpolar. And this is going to be a polar molecule. That lone pair of electrons and our geometry, our trigonal planar, is going to make this a polar molecule. When you go to list intermolecular forces, remember we said every single molecule has some London dispersion forces. If you know nothing else, write LDF. Everything has some LDF. Get you at least a point. Next, if it is polar, it automatically has dipole-dipole. And then next, we want to look to see, is there any hydrogen bonding? No, I don't even have hydrogen in this compound. So my answer would be LDF and dipole-dipole. Also, we're assuming that there would be a second molecule of nitrogen trichloride because remember, intermolecular forces occur between two different molecules. Let's say I had carbon tetrachloride. So again, first thing we want to do is look at it and decide if it is polar or nonpolar. Remember, when we're doing molecular polarity or overall polarity, think about those vectors. They are equal but opposite, so they are all going to cancel. This would be a nonpolar molecule. Two nonpolar molecules, two molecules of carbon tetrachloride, the only intermolecular force holding those molecules together would be LDF. LDF is the only intermolecular force acting on nonpolar molecules. Let's say I had, let's do this one. So again, step one. Is this molecule polar or nonpolar? Oxygen is much more electronegative. It's not symmetrical, or vectors aren't going to cancel. I am going to have a dipole moment. This is a polar molecule. Automatically, every single molecule has some LDF acting on it, holding it to a neighboring molecule. Since this is polar, it's also dipole-dipole. Lastly, we look to see, is there any hydrogen bonding? Here's where we have to be careful. Just because hydrogen is in the compound doesn't mean it's hydrogen bonding. Hydrogen has to be attached to oxygen, nitrogen, or fluorine. Well, I have hydrogen and I have oxygen, so do I have hydrogen bonding? The answer is no, because they are not directly attached to one another. Let's say I had something that looked like this. Step one, is it polar or nonpolar? this oxygen makes it polar. We're basing it off my central atom, which is carbon. All of my vectors are not going to cancel out. This is a polar molecule. Every single molecule, whether it is polar or nonpolar, has some LDF. Since this is polar, it also has dipole-dipole. And so the last thing that we look at is, will there be any hydrogen bonding? And there will be. So we're looking for that direct attachment. And remember, for hydrogen bonding, it is small electronegative atoms. Our options are oxygen, nitrogen, or fluorine. The other type of problem that you might get for intermolecular forces is ranking. Let's say you were asked to rank the following in order of increasing strength. And you're going to get 4 molecules. So the first thing that we want to do is go through each 4 of them, determine whether they're polar or nonpolar, and then determine our intermolecular forces. First one, again, think about your vectors. They're all going to cancel. This is a nonpolar molecule. So the only intermolecular force acting on 2 molecules of methane would be LDF. Think about your vectors. Based on the shape and based on this lone pair of electrons repelling and pushing it into this pyramid shape, this is going to be a polar molecule, ammonia. Everything has LDF. Since it's polar, it also has dipole-dipole. So lastly, we're looking, are there any sites of hydrogen bonding? Hydrogen to nitrogen. Nitrogen is one of the 3 elements. Oxygen, nitrogen, or fluorine. So this one also has hydrogen bonding. Next one, ethane. This one is nonpolar. Again, all of our vectors are going to cancel out. A little hint. The first one and the third one, we call them hydrocarbons. And we call them hydrocarbons because they're only made up of hydrogen and they're only made up of carbon. Hydrocarbons are always nonpolar. So that might help you, whether I give you CH4, if I gave you C3H8, if I gave you C10H22, rather than drawing out that molecule, anytime that it is only hydrogen and carbon, it is a hydrocarbon, it's always nonpolar. Last one. This one is not a hydrocarbon because it has a chlorine attached to it. That chlorine also makes it polar. These vectors are not equal in magnitude. Chlorine is much more electronegative than hydrogen. So this bond is much more polar. We're going to induce a dipole. Everything has LDF. Since it's polar, it also has dipole-dipole. So lastly, we want to see, are there any sites of hydrogen bonding? I have hydrogen, but it's not attached to oxygen, nitrogen, or fluorine. so there is not hydrogen bonding. So let's go with the strongest first. Hydrogen bonding is the strongest intermolecular force of the three. So that means ammonia, NH3, would have the strongest intermolecular forces. We said LDF is the weakest, dipole-dipole is a medium strength force. Alright, so what we have left are the two molecules that have London dispersion forces acting on them. Remember we said that as the size increases, the strength increases as well. Ethane is larger than methane, so that means it is going to be stronger. The more electrons we have, the more dipoles we can induce, the stronger that attraction is going to be. So, in general, London dispersion forces are weaker than dipole-dipole, which are weaker than hydrogen bonding. If you have two molecules that have the same intermolecular forces acting on them, then we go by size. Whichever one is larger is going to be stronger.